If you are a software developer, you must have heard of Kubernetes. Kubernetes helps us deploy large-scale microservices with just a few lines of commands. Kubernetes manages the lifecycle of containers, including their deployment, scaling, load balancing, and self-healing. We are going to deploy 5 microservices in the next few minutes using Kubernetes, so stay tuned until the end of the video. I can assure you that by the end of the video, you will have an understanding of how Kubernetes works and how to deploy microservices inside a Kubernetes cluster. Kubernetes can auto-scale microservices within a cluster based on criteria such as CPU or memory usage. If a service crashes due to exceptions like null pointer exception or out-of-memory exception, Kubernetes automatically brings up a new instance of the application called a pod. We will see this in action in the next few minutes. Let's first see what problem Kubernetes solves. Let's say you have a web service written in Java, and this service is going to handle a huge amount of traffic from the internet. Therefore, this web service needs to be horizontally scalable. This means we should deploy the service on multiple nodes, with each node running at least 2 instances of the web service. For example, if we have 2 nodes, then we should have 4 instances of the web service running across the 2 nodes. But what if one instance stops working due to some exception? Who is responsible for bringing up a new instance or restarting the existing instance? If traffic spikes, who will deploy additional instances to handle the increased load? Kubernetes solves all of these problems as a one-stop solution. Now let's look at the components involved in a Kubernetes cluster. This is a master worker architecture. The master manages the overall state of the cluster, while the worker nodes manage running instances of microservices. There are many components involved in the cluster, but we will focus on the most important ones. The Kube API server running on the master node serves as the entry point for all administrative tasks within the cluster. It receives commands either from the command line utility or through REST APIs. Based on these commands, various tasks are performed inside the cluster, such as deploying additional instances of a web service. The kubelet is an agent that runs on each worker node, communicating with the master to ensure that all containers are running. It also receives commands from the master to destroy or update existing containers. Each worker node also has a container runtime, like Docker, to run containers on this worker node. In short, the master helps manage the whole cluster, while the worker helps run actual microservices. In the last few seconds, I've used the word container a lot, which is understandable since Kubernetes is a container orchestration tool. It helps us run multiple related containers together and facilitates communication between them. I'm assuming you understand containerization concepts before we proceed further, so you must know what a Docker registry or Docker image means. What is public or private registry? How to create new Docker image of your application, and how to deploy it as standalone container. We deploy our microservices by creating API resources. There are over 30 resources in Kubernetes, but we primarily require just 4: pods, replica sets, deployments, and services. Each of these 4 serves a specific purpose. However, when we create all 4 for a given web service, we can declare that the service is deployed. If you have 5 microservices, then you will likely create 20 resources. The good thing is, creating these resources is very simple. Let's understand the purpose of each resource and create them one by one. Remember, every resource can be created either by providing all details on the command line interface or by declaring details inside a YAML file. Before we proceed to create our first pod, let's understand the setup on my local machine. Deploying a Kubernetes cluster on a local machine is a very complex task. To solve this issue, we have something called Minikube. Minikube helps us deploy a single-node Kubernetes cluster on our local machine. If you don't have Minikube installed, you can head over to the Minikube website and install it. Once Minikube is installed, we have 2 commands available to us. The first command is minikube, and the second is kubectl. The minikube command helps us interact with the Minikube cluster, which is just a Linux virtual machine, and kubectl helps us communicate with the underlying Kubernetes services installed inside the Minikube cluster. A pod is the smallest unit in Kubernetes, meant to run a container. Within the container, our application runs, whether it's a Java app, a database service, or just a shell script. While it's possible to run multiple containers inside a single pod, ideally, we run just one container per pod. Pods are designed to run and then be destroyed, so they typically have very short life cycles. Generally, pods are not restarted when they fail. Instead, a new pod is created to serve traffic. We don't scale pods. Instead, we run multiple pods for the same application. Let's deploy the Redis image available on Docker Hub as a pod. It's just a simple task. We just run kubectl run redis command. Let's see all pods inside our cluster. For this, we use the kubectl get pods command. Here, we can see our Redis pod is running happily. We can also see extra details like when this pod was created, how many times it was restarted, etc. Creating Kubernetes resources using command line options is not advised. Instead, we should write resources inside a YAML file. Let's delete our Redis pod using the kubectl delete pod redis command, and we can see the pod is gone. Let's create the same pod using a YAML resource file. All 4 resources that we are going to see will have 4 common properties in their YAML resource file: API version, kind, metadata, and spec. So, let's add these 4 into the YAML file. The value of API version will be v1, and kind will be pod. Metadata will have 2 properties: the name of the resource and optional labels. Here, the name will be Redis, and we'll add a few labels for our pod. The spec section varies from resource to resource, so for the pod kind of resource, we have a list of containers attribute. For most of the time, we specify only one container per pod. Here, we have our Redis container with the image Redis. This image will be pulled down from the Docker Hub registry by default. Our pod resource file is ready. Let's create the pod using this file. For this, we use the command kubectl create followed by the path of the file, which in our case is redispod.yaml. Let's get all pods to see that our pod was created in the last few seconds. So far, we have covered the basics of pods. We haven't yet discussed how this pod is accessible outside the cluster on ports or network interfaces, but don't worry, we will cover that in a few minutes. We just saw our Redis pod. But what if this pod crashes for some reason? Who will bring that pod back up? For that, we have a resource called a replica set. A replica set has 2 responsibilities. First, it creates multiple pods called replicas for a given container. Second, it ensures that all pods are running all the time. So, let's start by creating a new file called redis-replicaset.yaml. Remember, all 4 resources will have the same basic structure: API version, kind, metadata, and spec. The version will be apps v1, and the kind will be replica set. The metadata section will have a name and labels. Let's add the name and labels. Inside the spec section, we will specify the total number of replicas we want for this Redis service. Let's set this number to 3 for now. Next, let's add the template, where we will include the pod details. We will go back to our pod file, copy the metadata and spec sections, and paste them under the template. Finally, let's add a selector. The selector helps identify all pods that should be managed by this replica set. We will copy all labels from the pod section and place them under match labels. Now we have our replica set file ready. Let's ensure that no pods or other resources are currently running. Using the command kubectl create redis-replicaset.yaml, we can create a replica set. We can then retrieve the replica set by executing kubectl get replica set. Here, we can confirm the existence of our replica set. The desired number of replicas is 3, which matches the current count, indicating everything is functioning properly. Additionally, the count of replicas ready to serve traffic is also 3. Thus, we are all set. Now, where are the pods? We can verify their existence using the command kubectl get pods. This command reveals that 3 pods are indeed running, each bearing a suffix identical to the name of the replica set. Hence, we can ascertain that these pods are managed by our replica set. Now let's delete one pod. The replica set should bring up a new pod as soon as we delete one because that is the basic responsibility of the replica set, to keep all pods running all the time. Let's delete one. Use kubectl delete pod, followed by the pod ID. Now let's check all pods once more. We can see that the age of one pod is just a few seconds, which means this is a new pod created by the replica set to match the desired pod count. Now that we've solved half of the problem, the next step involves addressing what happens when a new version of the Docker image becomes available. How do we deploy those latest changes? In this scenario, we need to utilize the deployment resource. Do we stop all pods and then deploy new pods? Will there be downtime? What if we deploy one pod at a time? Additionally, if the newly deployed container has some bugs, how do we roll back to the previous version? The answers to all of these questions lie within the deployment resource. Let's create a deployment resource YAML file. As a starting point, it will be an exact copy of a replica set, with the only change being the kind field. One important point to note is that when we create a deployment, Kubernetes automatically generates a replica set under the hood, and the replica set, in turn, creates pods automatically. We can use the kubectl getAll command to verify that we don't have any active deployments, replica set, or pods. Using the kubectl create command, we will create our deployment. Using the kubectl getDeployment command, we can see our deployment. Let's use the kubectl getAll command to see everything created by the deployment. Here, we can see our replica set and all 3 pods running successfully. With the deployment resource, we can manually trigger deployment using the rollout command. Also, we can roll back the current deployment to the previous one using the undo command. We can see all these revisions to the deployment using the history command. Let's trigger the deployment manually using kubectl rollout restart deployment Redis deployment. Here we provide deployment name as an input. Now if we fire kubectl getAll, we can see old pods going down and new ones coming up. This is called a rolling update strategy. Only one container goes down at a time, and the others remain up to serve traffic, so our app is always available for end users. Let's see the history of the deployment using kubectl rollout history deployment Redis deployment. Here we provide the deployment name as input. Let's undo our latest deployment because it has a bug, and we want the older version of our app to be up. We can use the kubectl rollout undo command for this purpose. Now we can see some pods going down and new ones coming up. So this is all about deployment. Everything is good except our app is not accessible to end users because we haven't configured how our app is available on ports outside the cluster. For this purpose, we have a 4th resource called a service. We mainly have 2 types of services in Kubernetes, cluster IP and node port. When we want our app available outside the cluster, we create a service with type node port. Services created using type cluster IP are accessible only inside the cluster. Let's deploy a simple microservices architecture using Kubernetes. While doing so, we'll delve into understanding more about services. We have a voting app where users can cast their votes for either cats or dogs. Votes are recorded using the voting service, and the results are displayed using the results service. The voting service initially sends vote information to the Redis service, which serves as an in-memory database. Additionally, there is a worker service that retrieves votes from Redis and stores them in the Postgre service. Finally, the results service reads votes from the Postgre service and displays them on the user interface. To implement this, we only need 2 Kubernetes resources for each service. We will create 1 deployment resource and 1 service resource for every service except the worker service. Since no one accesses the worker service, we don't have to open any node port for it. Therefore, we just need a deployment resource for the worker service and don't need a service resource to expose the port. Let's proceed with creating 5 deployments for our 5 services. We've already observed and tested the deployment of Redis. Now let's modify the label of the app here. Since this Redis service will be a part of the voting app, we'll change the name of the app to Demo Voting App. We want this Redis service to be accessible to other services inside the cluster. To make it happen, we need to open the port for this Redis service. We'll open port 6379 for this Redis service. Now, we are done with the Redis deployment file. To save time, I've already prepared deployment resource files for the remaining services. Let's go over a few important points in each file. The Postgres deployment resource will have the same structure as the Redis file, except for a few additional environment variables needed by the Postgres image. The Postgres service will be available on port number 5432. Note that the Postgres and Redis images will be downloaded from Docker Hub and are ready to use. We need to write a deployment file for the vote, result, and worker services. I have already built and pushed images of these three services into the local Docker registry. Instead of downloading images from Docker Hub, these images will be downloaded from the local registry. Therefore, every image is tagged with an IP address. The result and voting services will be exposed on port number 80, and the images of these services will be downloaded from the local registry. No one needs to access the worker service directly, as it reads data from Redis and writes to Postgres. Because of this, we won't expose any port for the worker service. Now we are ready with all 5 deployment resources. Let's create them one by one. First, create the Redis deployment. Second, create the deployment for Postgres. Next, create the deployment for the Vote app. After that, create the deployment for the Result app. Finally, create the deployment for the Worker app. Let's check our deployments using the kubectl get deployments command. Here, we can see we have a total of 5 deployments. Next, let's use the kubectl get all command. We can see we have 5 replica sets, one for each web service or database container. Finally, we can see all pods are running successfully. The question now is how we access the Vote and Result app. To do this, we need services. Remember, we don't need a service for the Worker app, so we need a total of 4 services to be up. The Voting and Result services will be of type node port, and the Redis and Postgres services will be of type cluster IP. I have already prepared service resource files for all 4 services. Let's look at the service file for Redis. The type of service is cluster IP because we don't need Redis to be exposed outside the cluster. We have specified ports here. The port refers to the port of the service, and the target port is the port of the pod. Any traffic sent to or received from this service will be redirected to the target port. The host name for Redis will be Redis, which is the name of our service, and the port will be the service port. Traffic will be forwarded to the target port, but to which pod's target port? This is where the selector comes in. All pods with labels that match those specified under the selector will become part of this service. We have another cluster IP type service for PostgreSQL. The port number, name, and labels will differ here. For the voting app, the service type would be node port. In this case, we need 3 ports: the node port, the service port, and the pod port. Traffic received on the node port will be sent to the service port, which will then forward it to the pod port. The service for the result app would be similar, except for changes in the port values. Now that we have the files ready for all services, let's create these services one by one. First, we will create the service for Redis. Second, we will create the service for Postgres. Next, we will create the service for the voting app. Finally, we will create the service for the result app. Let's enter the command to see all the services we just created. We can see all 4 services are visible here. Kubernetes clusters only work on Linux, but thanks to Minikube, it is possible to run Kubernetes on Windows. To access our voting and result apps, we need to create a tunnel using the Minikube service command. This command opens a tunnel for a specific service, but we must keep our terminal open for this. We can see our voting service exposed on a different port through the tunnel. Let's open a tunnel for the result service as well. For the result service, we get a specific URL. Let's open both addresses in the browser. First the voting app, and then the result app. We can see both apps loaded inside the browser. Let's vote for cat and see the result instantly in another window. Let's change the vote and see the updated result. This demonstrates our entire microservice architecture with Kubernetes working perfectly. This is all about Kubernetes. It took me a lot of time to make this video, so please like it to help the YouTube algorithm share it with more people. If you haven't subscribed, please make sure to subscribe to this channel. Thank you.